Hi, my name is Surush Abbasi. I'm presenting our work Self-Supervised Learning by Iterative Similarity Distillation. This is a joint work with Ajinkya, Weapon, Paolo, and Hamed. The goal of self-supervised learning is to learn rich representation with only accessing to unlabeled images or videos. Pre-trained representation using SSL methods can be used as an initialization and transferred to downstream tasks where annotated data is limited. Recent state-of-the-art methods in SSL use contrastive learning. They train a model to pull two different augmentations of an image to be close together and push them away from other images. In contrastive loss, other augmentations of an image are positive set and some random images are negative set. Standard contrastive learning has a binary distinction between positives and negatives. While positive samples are semantically related, not all negative instances are equally negative. For example, some instances in the negative set might be semantically similar to the positive instances. Our goal is to relax the binary distinction between positives and negatives in contrastive learning by assigning soft labels to negatives. Now, the question is how to assign soft labels to negatives. In recent self-supervised models, it's popular to train two different encoders, where the second one is exponential moving average of the first one. In our work, we call moving average encoder as the teacher and the other encoder as the student. We study the accuracy of the teacher and student in recent SSL methods. Interestingly, we observed that the teacher is consistently better than the student during training. We believe the teacher has better accuracy since the teacher is temporal ensemble of previous student models. Since the teacher has better accuracy during training, our idea is to use the teacher as a source of knowledge to assign soft labels to negatives. Inspired by compressed, we do unsupervised knowledge distillation without pre-trained teacher. On each iteration of training, we distill the knowledge from the teacher to the student by predicting the soft labels of the teacher over anchor points. Note that we initialize both teacher and student with the same random initialization and train them from scratch. Here, we visualize positives and negatives of a self-supervised learning during training. We sort the negatives based on similarities to the positive set. By looking at the negative set, we can see that many of them are semantically related to the positive set, yet the model pushed them away from the positive set. Unlike a standard contrastive loss, our method assigns soft labels to negative set. Hence, we will not treat all negative points equally. In more details, for a given query image, we augment the image twice. We also have a set of random images which will be used as anchor points. Then we forward the first augmentation of the query image and anchor points to the teacher encoder. We calculate the similarity of the teacher's query to anchor points and pass similarities through the softmax to get probability distribution over anchor points. Next, we forward the second augmentation of query image through the student encoder followed by prediction layer. Same as the teacher, we calculate the probability distribution of a student's query to anchor points. We train the student to minimize the KL divergence loss between two probability distribution and update the student with gradient descent. Finally, we update the teacher as a moving average of students' parameters. In ImageNet experiment, we train our model with 200 epochs on unlabeled ImageNet with reset 50 and reset 18 as a backbone. To evaluate our model, we freeze the backbone and train a linear classifier on ImageNet training set and report top 1 accuracy on ImageNet validation set. Interestingly, our method is more than 2 points better than MoCo as a standard contrastive learning and outperforms BYUL. ISD outperforming MoCo empirically supports our main motivation of improving representation by smoothing the contrastive learning and not considering all negatives equally negative. Moreover, our method outperforms both BYUL and MoCo with reset 18 backbone. In ImageNet limited labels benchmark, we fine-tune our pre-trained model with only 1% and 10% annotated ImageNet data. Our reset 50 outperformed BYUL and MoCo in this benchmark. Note that we only train a single linear layer on top of frozen features. Thanks for your time. See our paper for more details.